Hey everybody, this is Larry. This is Leetcode Contest 195. Well, the contest kind of had issues, so there was no live stream, or live cast. I did record it, but it was just janky and it's all over the place. I might put it up later, but for now, I just want to focus on the explanation so you have a chance to, well, give yourself a hint to practice and so forth. And as you can see on the top, Weekly Contest 195 will be unrated. But I had fun. So the first one is pathfinding. So this one, given that n is only up to 10 to the fourth, which is 10,000, you could actually put everything in a hash table, right? And because every movement is in an integer point, you just have to keep track of it. So if you go north, you move x plus 1. If you go south, you do x minus 1 and so forth. And then you just put everything in a hash table. And then at the very end, if you see the same point more than once, then you return true. If you don't, then you can return false at the very end. So that's the Q1. This is O of n because for each node, you look at it once. It is O of n space because you put in a hash table. This is assuming the hash table is all of one insertion and stuff like that and lookup, which you could debate however you like. Another thing to note is that I know that I said that x is plus 1 and x is minus 1 for north and south respectively, but it actually doesn't matter as long as you're consistent, because you can think of it as that if you got it a little bit backwards, then you just flip it's a mirror image, right? So in one of the two directions. So it doesn't actually matter. So you can definitely get it correct in this way. So that's Q1 explanation. Q2, check if array pairs are divisible by k. So this one, you want to divide an array to exactly n over 2, right? So I guess actually you should have probably checked that n is even. Okay, n is even. But the idea here is greedy. What do I mean by greedy? What I mean by greedy is that anytime you can match two numbers, you match the two numbers. And so what I did is that for every number, I converted to the number mod k, because that means that when you mod it by k, when two numbers add to each other, then they'll sum to k or 0. And that's pretty much my algorithm. So I do a count of I keep track of a count of all the array elements, mod k. And then if 0 is in the array, if 0 is in the counter or the hash table lookup, then we check that as a even number, because if it's odd number, then there's no two numbers to match with the zeros, because then you don't match. Though I think it actually ends up not mattering, because by the pigeonhole principle, that means that another number is not matched. But here, if x is greater than 0, then we just check that a sub x is matched with k minus x, right? And what that means is that, for example, if you have a number, let's just say, you have 1, 2, 3, 4, 5, and you can actually think of this as just actually odd evens, so that you could phrase it that way. So if you have odd even numbers, then, like for example, if k is 2, then the number of even numbers have to be even because they have to match with each other, and then the number of odd numbers also have to be even because they also have to match with each other. Actually, maybe I messed that up for even numbers. Somehow it's still passed, but maybe that's just a little bit lucky. Because I think if x is equal to k minus x, you may have to check that. But I think it's also one of those pigeonhole principles. Why this accidentally works is that because if it's odd number, that means another number has an odd pair out, and that's why this works. But you should be more careful and not did what I do. But let's say you have number 3 mod, right? Let's say k is equal to 3, then you just mod everything by 3, and you have 1, 2, 0, 1, 2, 0, right? So now we group them together. We have the 2 1s, the 2 2s, and then the 2 zeros. Oops. Right? And then because this is even, they all match with each other, they live happily ever after. And then the rest is that that if you have a 1, you need a 2 to make the sum of the pair of them equal to 0. So that's pretty much the idea behind if they're equal to each other, then if they're not equal to each other, then you can match them in any other way. So the complexity of this is going to be O of n, because for each element you put it in a hash table, and then for each key, which is less than k, to be honest. But for each key, you just do these O of 1 checks, and that'll give you the answer. And actually, you don't even need a hash table. You could have used an array, but you know. And in terms of space, this is O of n for this set reason of this hash table. Yeah, so definitely an interesting problem. It's greedy, and there's some hash tables, so I guess definitely practice this for your interview. I dig this problem. Okay, cool. Q3. Yeah, number of subsequents that satisfy the given sum condition. So this one is actually, I did like this problem. It's a little bit tricky, but it's still, I dig it. And basically the problem for for this problem, yeah, there are a couple of ways to think about it. The way that I thought about it is that, for example, well, first of all, you sort because why not sort? And it's, for n is equal to 10 to the fifth, sorting will be fast enough. But let's say after you sort, then you want it to have some target that it is smaller than, right? Well, now you're going from left to right. Let's say the answer is, I think in this case, it's, okay, 12 is a little bit big, but maybe that's fine. Let's just say this is 9, right? Well, for 2, then you do a binary search for the number that is, that lets you do, you find the index so that the sum between that number and the target is less than this. So in this case, it'll be 2 to the 7. And the way that I structure is that I am forced to have a 2, right? So now that means that all these other numbers are free in that it could be 0 or 1, right? So because you only care about the max, and you know that the max will be 7 in this case, and any number that's smaller than 7, let's say you have a subset. So if both 2 and 7 are in the subset, then you know that the target is, the sum is going to be equal to 9 of the max and the min. But let's say it's less than 7, right? Let's say your sequence is, this, right? Then, well, this, that this is going to, the sum between the min and the max, and it's just going to be 6, which is smaller than the target, because this max number is already going to be bigger than that number. So in that way, the size, the length of this sequence, without the 2, every number could be just, it could be 0. When I say 0 or 1, I mean like every number in here could be in the set or not in the set. And because in this case there's 5 numbers, so that means that there's just 2 to the 5th case. Oops, 2 to the 5th case where, so there's 2 to the 5th case where this is true. The thing that I handle a little bit differently, or you have to be careful about, is that, well, if these cannot all be not in the set, because if these are all not in the set, then you have to look at the first number twice. And then I handle that. So we subtract 1. This is why I have to subtract 1 here. I subtract 1 so that it doesn't count the case where they're all not in the set. And then I do a separate check, which is, if 2 times 2 is less than target, then I add that set back in. So that's how I do the summing. And I do a mod. And in your language, you have to do a mod pow, a power that's mod, and that will make it a lot easier. And then, and then you just kind of keep on going as you go left. So for example, in 3, well, you do a binary search, and the binary search should tell you that it's actually, 6 should be good. And actually, now that I think about it, you actually don't even need the binary search. You know that it converges, from left to right. So you could have just a right pointer that goes from right up. So yeah, but binary search allows you to kind of think about it without worrying about certain things. That's how I thought about it. But yeah, but you can actually just move. You can have 2 pointers that starts, at both endpoints, and then move slowly toward the middle to make sure that the invariant is that the sum is less than 9. I actually didn't think about that, but until just now. So whoops. But binary search also runs in time. It's n log n. But if you actually did it now with this linear algorithm, then it'll be O of n, because every element will be on the left side or the right side only once, right? And yeah, and once you go past the middle, you just have to check, the target, the number times 2, and that's pretty much how this algorithm works. And yeah, so you could do it in n-log n if you did it like I did with binary search, but as we actually discovered together, you can actually go from right to left, so it's O of n. So this makes it an O of n algorithm, which is fast enough. And yeah, oh, sorry, I forgot about the sorting. So you do have to sort, so it is going to be n log n plus the O of n. So I guess in that sense, it doesn't really matter, but it is still O of n log n. But if the array is sorted, then you just go left to right, right? So, and right to left. So that'll be still faster for that reason. For space, it is, you could see that we don't use any extra space, or like we use constant amount of extra space, with some caveat around sorting in your native language. So yeah, but mostly all of one say, right? Extra space. So that's kind of Q3, number of subsequents that satisfy given some condition. Q4, max value of equation. So this became a mono Q max Q algorithm. I'll have a link below to my explanation of how to solve mono Q problems. But the tricky part, and it is not easy, is recognizing that. So one is that the X are sorted. So I actually try to sort first, but it's not necessary because it's already sorted. But as you kind of go from left to right, you're trying, what this looks like is that even though this formula is like this, oops, I think that's the part that I struggled with a little bit when I was looking at it. So you have this formula, but actually since I is less than j, and we were told that x of I is less than x of j, you can actually rewrite this as x of j plus x of j minus x of I, right? And then now from that point, you can separate out the x sub i's and the x sub you could separate out the j's, so that looks like this plus this, right? Yeah, and so here, so now you have this element as you go from left to right, using a mono Q or a monotonic Q or a max Q, right? So now you're giving this number and a max Q. All you have to do is take the max element and then add it to the current element, and when you put it on the Q, just put this sum back in, and that's how you do it. The implementation may be a little bit tricky. Again, check out my mono Q video. I didn't even solve it that way. I did the mono Q, but I did it with a heap because I wasn't quite sure why I was solving it. There are a couple ways to do it. I also described this way of solving it on that mono Q video, so check it out. But yeah, but now that you've written it this way, this is the thing that you're trying to get the max, and as soon as x sub j minus x sub I is greater than k, you remove it from the mono Q, and that's how you solve Q4. Pretty straightforward once you do this formula manipulation. It took me a little bit long because I didn't make the connection, but yeah, that's all I have for today's contest. Let me know how you think, let me know how you feel, let me know your favorite question, and I will see y'all next contest. Bye bye.